We're going to talk about vectors as linear combinations. What we're going to do here is we're going to figure out what scalar multiples we need to use on these two vectors to create this vector or an equivalent vector to 4 and 23. So the idea is we're going to need to multiply our vector A by some scalar multiple. We'll call it, maybe I'll actually call these x, y, and z. So we'll call our scalars ABC, just so we don't get too confused here. That's what we do before. So x, vector y, vector z. We're going to create vector z. So our scalar multiple of the first one is we're going to have A multiplied by 1 and 4, and some B, sorry, it's a comma here. B is some multiple of 2 and 5, which will essentially create our 4 and 23. Okay? So what we'll do is we'll use distributive property. We'll multiply our A in, and we'll multiply our B value in to find out what scalar multiples will work for this. When we go about doing that, we're going to have negative A and 4A. This is an x and a y. Okay. And we're going to have 2B and 5B. That's kind of like our x and our y coordinates here, are going to be equal to 4 and 23. So really, our like terms here, these are our x values. Those are the values or the scalar multiples we're going to use to create our 4. And these are our y values. So what we're going to do is we're going to build equations out of them. We're going to have negative A plus 2B is equal to 4. That'll be our first equation. And we're going to have 4A plus 5B is equal to 23. Now what we're going to do is we're going to use substitution or elimination, whatever you're more comfortable with, to solve for our scalar multiples of A and B. We'll get these values by just using some type of substitution. I think will be easiest. So I'm going to set this equal to A. So that'll be my first equation. We'll do it in red. Let's not do it too fast. I made that mistake yesterday. It's equal to 4 minus 2b, which is A is equal to negative 4 plus 2b. Okay, so now we have a value for A, which means we can now plug it into our second equation for that A value. 4 multiplied by negative 4 plus 2b plus 5b equals 23. This will give us negative 16 plus 8b plus 5b is equal to 23. This will give us our 13b is equal to 23 plus 16, which gives us 13b equals 39. B is 3. So the scalar multiple for our second set, B here, will be the value of 3. This goes really slow. Okay, we still have to find out our A, so we'll go back to the bottom again and use substitution. Just a little. We can again go back to equation 1. Negative A plus 2. This time we can substitute in for our value of B because we have the number 3. There we go. I was wondering if it was going to show. Is equal to the value of 4, I believe. This gives us negative A plus 6 equals 4. Negative A equals negative 2. A is the value of 2. So the scalar multiples that we'll need for this equation, our 3 and 2. And let's say I needed to represent that as an equation with maybe unit vectors. Okay, we know that our first one is 2 and whatever our coordinates were, and the second one is 3 and whatever our coordinates were. So if we were to use our scalar multiples of unit vectors, negative 1, 4, and 2, and 5, negative 1, 4, 2, and 5. Okay, we know that these are the multiples we need to create 4 and 23. If they ask us as unit vectors, you could say your idea is that this would be our I. So we would have 2 of the value of negative I and 4k. And our other equation, we have 3, 2i, and 5k. Oh, sorry, you're right, it is j. I. Sorry, 1 second. Oops, j and j. Okay, and we would just use our scalar model. We'd use our distributive property to get right back in. So we'd have our two equations as unit vectors. So negative 2i plus 8j, and our other equation being 6i plus 15j.